Hello again. We are going to discuss now more advanced topics about curves. We will focus on the computation. The derivation of the formula will be discussed in class. So the main objects we want to calculate is the curvature. Now, just from the name, curvature means some kind of measurement of curviness of a curve, right? And here we have the formula. First of all, we try to understand why a curvature should be the derivative of the unit tangent vector. This is really important one, unit tangent vector. We already know that tangent vector is the derivative of your position function. So this is tangent vector. But tangent vector contains other kind of informations. If we make it a unit vector, this is called t of t. And that's going to be r prime t divided by its length. Then we are focusing only on the direction of the tangent vector. And how fast this direction of the tangent vector is changing is precisely the curvature. But we need to do actually two things. One, we use the unit tangent vector. Two, the change of the direction has to be with respect to the arc length, not just arbitrary parameter. So the formula is a little bit complicated. It involves the cross product of the tangent vector and its second derivative. If you think about second derivative, it's the acceleration rate and divided by I prime of t cubed. So how can we reason this is the right formula? We can think about this. This is just a heuristic one. We remember that t of t is r prime of t to the power r prime of t, right? So if you take the derivative, you need to use the quotient rule. Of course, here we're going to have the denominator over here squared, right? And then we have things on top, okay? So that's reasonable to have this kind of formula. We have over here r prime of t cubed, and then on the top we have r prime of t and a cross product of double derivative, okay? All right, the rest of this summary we will mention when we actually encounter them. So let's focus on the example one over here, the example one. Okay, we're going to write down the solution. Okay, sketch a diagram of this helix. We did this in the past, so we're going to do it rather quickly. Okay, so this is going to be 2, this is going to be 2, and we have something like this. Okay, and here is 45 degrees, so this is the point. Okay, and we can write down even the coordinate of p when t is 1 pi over 4, then we have 2 cosine pi over 4 and 2 sine pi over 4 and pi over 4. If we simplify, that's going to be exactly square root of 2, square root of 2, and pi over 4. Okay, so that's the point we are looking at, this point P. Okay, and we want to find the curvature over there and unit tangent vector, the normal principal vector, and the binormal vector at this point. Quite a lot of things to find, but the way we start over here is look at r prime of rt. Rt is 2 cosine t and 2 sine t and t, right? So we take the derivative, and that will give us the tangent vector. So this is going to be negative 2 sine t and 2 cosine t and 1. So this one over here is tangent vector. but it's not the unit tangent vector yet. So we're going to look at the length over here. This vector's length is a square root, right? So we have -2 sine t squared plus 2 cosine t squared and plus 1 squared, right? And that's the one, the vector's length. And we have square root over here. We have 4 cosine squared t and plus 4 cosine t squared and plus 1. And then we will have square root of 4 plus 1, and that's going to be root 5. Okay, so that's the length of this vector. So now we have the unit tangent vector. Unit tangent vector is r prime of t over its length, and that will give us 1 over root 5, and here we still have -2 sine t and 2 cosine t and 1. That's the unit tangent vector at any point. So at P, we will have, that's when t is equal to pi over 4, we have this capital T of t is equal to 1 over root 5, and this one is going to be negative root 2 and 2, root 2 and 1. At each point is it's a fixed, right? So we have found 1. What is the unit tangent vector at this point? Okay. Now, to find the normal principal vector, we take the derivative of capital T. But let's just wait for a moment. Let's try to see if we can find the curvature now. Okay. To find the curvature, we have kappa over here is equal to the length of r prime of t cross product r double derivative, and then divided by r prime of t cubed. We already know the denominator, right? So now we just need to find our double derivative. We go back, and that's going to be -2 cosine t and -2 sine t and 0. Okay, so now we're going to find the cross product. It's a long computation, so this is pretty long. We have I, j, and k. Because we are taking the length, it doesn't really matter which one first, but let's put RT first, derivative. So -2 sine t and 2 cosine t and 1. And then we have -2 cosine t, -2 sine t and 0. So we haven't done this cross product for a while, so let's try to see if we can still remember. For the I component, we're going to have 2 cosine t times 0, and this one is negative, but it's become positive. So we have 2 sine t I. Okay, this is not dot product, it's just notation. And for j, remember we have this one over here. Let's just try to remember the formula, and then plus k over here. We skip the first one. For j, we have -2 sine t, -2 cosine t, and we have 1, 0 over here. And for k, we have -2 sine t, -2 sine t, and 2 cosine t, -2 cosine t. So we now have 2 sine t I, and this one over here again we have gonna have negative. Now this one over here becomes positive, so we're gonna have 2 cosine t j, and then we have over here we have 4 sine t squared and have 4 cosine t squared, because negative becomes positive, and that's k. So it's not too bad. In fact, we get this one over here is 2 sine t. If we use this vector notation, negative 2 cosine t, and this is exactly 4. Okay. Now to find its length, so this is r prime of t cross r double prime of t, right? And then we try to find its length, okay? And this one over here, that's the square root 2 sine t squared plus negative 2 cosine t squared and plus 4 squared. So now we have over here square root 4 sine square of t. We can see it's also 4 over here. So we again see this nice formula, okay? And that would be 4 plus 16, and that's going to be root 20. Okay. Now it's time to put everything inside. So kappa is going to be root 20 divided by root 5 cubed. And that's going to be equal to 5 root 5. And here we have 2 root 5, right? So that's going to be 2/5. And that's going to be the kappa. So this is the curvature. You may say, what does it mean, curvature? We actually are going to explain that one, the curvature. The smaller the curvature is, the straighter the curve is. So if curvature is 0, that means there is no curvedness, a straight line. If curvature is big, that means the curve is really, really curvy. Okay, so that's the curvature's meaning. It's how curved we say a curve is. So now we have had curvature, unit tangent vector, and now we want to find the normal principal vector and the binormal vector. I think I'm gonna just give you the formula for the binormal vector instead of computing it, because otherwise the video is gonna get really long. Okay, so the normal principal vector, that's the derivative of t. The normal, or it's principal normal vector. Principal normal vector. And that's the t, the unit tangent vector's derivative. Okay? If you want to have the principal unit normal vector, then you're going to take the derivative and divide it by its length again. But this one over here, we're just going to take the derivative. Let's try to see what capital T of t is. We found it back over here. This is the one we have. Okay, so it's 1 over root 5, then negative 2 sine t, and positive 2 cosine t. So this one over negative 2 sine t and 2 cosine t. And the last component is simply 1. So when we take the derivative of that, it's going to be 0. So this one over here, constant can be pulled out. So it's 1 over root 5. And then this derivative over here is negative 2 cosine t. We remember we already calculated when we were doing the curvature, right? Negative 2 sine t and 0. So this is the one. Now, how about, or we can just drop the 1 over root 5. That's going to be also okay, because we just want a normal vector. So what is the binormal vector? Binormal vector. We just use we can simply use r prime of t cross t prime of t. Okay, and that's the one we have. All right. So I'll skip the computation for the last one, as we said. Now, about the principal normal vector, this is for any point along the curve. You can also say at t is equal to pi over 4 t prime pi over 4. That's going to be equal to 1 over root 5. And then here we have negative root 2 and positive root 2 and 1. Okay, so that's the principal normal vector. Okay. All right, now let's go back to see if we have anything else over here for this problem. So we've done unit tangent vector, curvature, the normal principal vector. I think I reversed the order. It's supposed to be principal normal vector. And binormal vector, and this one. And here's the interesting part. Sketch the graph of the osculating circle at this point. Now, what is the osculating circle? That's the circle fits best in the concave side of the curve at that point. So let me change the color over here to a purple. So what we have over here, if you try to draw a circle on the concave side, this radius r is supposed to be 1 over kappa, the curvature. And then you can try to draw a circle like that. And this one over here is called the osculating circle. Okay. And it is an interesting thing how you can find its equation, because again, it's a space curve, and we will talk about that one in class. Okay, so here again, let's recap what we have over here. Start from the position function over here. We have first the position r of t, the curve, and if we take the derivative, we get the tangent vector. Okay, and if we divide the tangent vector by its length, then we get the unit tangent vector. This is called t of t, the unit tangent vector. Now, unit tangent vector, if we take the derivative further again with respect to the arc length, then we have the curvature. So over here is the curvature, and the formula is given in the textbook, and the derivation is not long. We're going to discuss that. So, and if we look at the derivative of the unit tangent vector and cross product with the tangent vector itself, here we know that the tangent vector is always perpendicular to the unit vector's derivative. So we already have two vectors that are perpendicular. If you make a third one, then we have three vectors that are mutually perpendicular. And this is a very nice so-called coordinate system along a curve. That's all we want to have.